In statistics, there are actually many types of things we might want to test. We're just starting, getting our feet wet. But one very similar thing to testing, doing a bootstrap hypothesis test for one population mean, is doing a bootstrap hypothesis test for one population proportion. And we call this symbol pi, not to be confused with the 3.14159, the one the pi that you're used to. Pi is just a Greek symbol. Remember, we use Greek symbols to denote things about our population, and the corresponding English letters to denote things about our sample. So a proportion, let's look at this example. A researcher tests to determine whether the proportion of patients coming into the emergency room complaining of chest pain has changed from the previous report of 30%. He is interested in testing this hypothesis at the 10% significance level. In a random sample he conducted of 100 patients, 40 of them reported chest pain problems. Okay, so first of all, notice that there's nothing about means. There's actually no raw data or measurements collected that are, like heart rates or anything like that. So in this case, I'm just going to draw out our population, our sample, the idea of what exactly we're doing here. We're drawing from a population, creating a sample, and what we're doing is we're calculating a proportion. So in this case, what we would call P, the proportion of people in our sample with a certain characteristic. We have 40 out of 100, which is equal to 0.40, or 40% of the patients in the sample reported having chest pains. Now, it's believed previously that mu is equal to 30%, which is 0.30, and we want to see, is that a big enough, does our sample indicate a big enough difference from our null hypothesized value to believe that, in fact, more patients are coming in? But keep in mind that he didn't know whether it had gone up or gone down. He just he asked the question of, has it changed? So that doesn't indicate a direction, which means this is going to be a two-tailed test. Meaning we're going to allow for the possibility that really, once we've collected our data, that it might have gone up or gone down, but we have no reason to suspect one way or the other. Again, keep in mind that we don't really know the sample data until after we've done our sample. Okay, so how is this different? Well, first of all, this is a very simple calculation, right? It's just you took 40 divided by 100. You didn't have to add anything up and divide. So it's not really a mean, it's a proportion. So what are we collecting from our clients, or collecting from people? Well, really what we're doing, if you think about it, we're collecting one of two values. The x value that we get from a person is going to be 0 if no chest pain, right? So in other words, of those 100 patients, 60 didn't, there are 60 values not tallied in here. But for each person that reported chest pain, we recorded a 1. So really people's responses are 1 or 0. They had it or they didn't. And so if you look at this, you had 60 zeros and 40 ones, and when you add those up, that's 40 points total out of the 100 respondents. So really what this is that I have 60 zeros, so 0, 0, 0, 0, etc. And I'm going to have a total of 60 of those, right, in my sample. And then I'm going to have 1, 1, 1, dot, 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 1. And I'm going to have 40 of those 1s. So in a way, it's much the same way as dealing with data, except my data here are 1s and 0s instead of actual numerical values that are kind of continuous scale. So here's kind of our motivation for how do we test to see if this has significantly changed. Well, it's going to go by way of Bootstrap. So here's what we're going to do. Assume H naught is true. Okay, that is, in other words, that 30%, that basically pi is equal to 30%. And see, I did it over here. I said I wasn't going to use mu, and I did it anyway. Just a bad habit. So pi is equal to 0.30. That's the symbol. And this is just a Greek p. This is an English p. So we want to test whether h naught, mu is still, or pi is still equal to 0.30, that 30% of patients come in with chest pain. Now again, our sample indicates 40%, but we're going to expect that from every 100 patients, they're not exactly going to all report the same thing. So how are we going to do this differently? Because remember how we recentered our distribution to be at the null hypothesized value. So our idea here is, since we're assuming h naught is true, we're going to say, okay, if we have 100 people in our population, we would expect that 0.30 or 30 people expected to report a 1. Right? That's what we would expect based on the null hypothesis. So that means that in a sample of 100, we would expect 70 zeros and 30 ones. So what I'm going to do is I'm actually going to create this. I'm going to have 0, 0, 0, 0. I'm going to have 70 of these. And then I'm going to have 30 ones. And I'm going to resample from this. I'm basically going to treat this like a 100-sided die, and I'm going to roll it 100 times, and I'm going to repeat that 10,000 times and see, that'll basically give me an idea of all the different sample proportions we should get. So basically, I'll write it this way: 1, toss 100-sided die 100 times. 2, record the sample proportion P, and then repeat steps 1 and 2 10,000 times. Total times. So that basically I can kind of see, because in some samples I might get 40 ones and 60 zeros. In another sample I might get 50 ones and 50 zeros. I just want to see what we would expect to be completely normal. So I actually have a built-in function into R to actually generate all these zeros and ones, which is very simple to use. So first of all, we're just going to state our hypotheses. We're trying to figure out, I keep using U again, whether the population proportion is in fact still 0.30 or whether pi is no longer equal to 0.30. We're not testing directionally, we're just trying to see if in general it's changed. So if we generate this distribution, which guess what, it's going to be normal again, and we center it at 0.30, what are our cutoff points? In other words, our sample of 40%, does it lie here or does it lie out in the tail? So I'm going to do this, and I'm going to go over to RStudio, and I'm going to run this. And the function that I built that will now be able to allow you to generate these, just so you don't have to type in 30 ones and 70 zeros, is you're going to run this x less than dash, and it's called propgen, which just stands for proportion generator. Let me actually clear this out. Clear workspace. I didn't actually want to do that. I actually wanted to clear this. Okay, so now I'm going to type in x less than dash propgen, and all that's going to do is it's going to ask me 2 questions. How many trials? Well, I have 100 people, and how many ones? I want to have 30 of them. And now you'll notice that it created this vector over here, and if you actually looked at x, you'd notice that there are, in fact, if you counted, there are 30 ones, and there are going to be 70 zeros. It doesn't look like it, right? But yeah, there are 70 zeros, 30 ones. Okay, so now I'm going to run things as usual. I'm going to do x resample, and all I'm going to be resampling is ones and zeros. So let's see here. Okay, I've actually changed that. I made it a little bit easier. I had to pause for a second. So actually what we're going to do is, instead of running this, because it got a little complicated, so what we're going to do is we're still just going to run our resample, but what we're going to feed the resample function is, in quotes, propgen. And that's going to ask us a couple additional questions before it continues to run. So all I'm doing differently is I'm just going to type in x resample, and then if I want to generate these proportions, I'm going to do propgen. And it's going to ask me how many trials. I'm going to say I have 100 trials. I want 30 ones, because that's my null hypothesized distribution. And now it's going to ask me how many times should I resample. So basically what it's going to resample from is from the 30 ones and the 70 zeros that are going to be generated. What should the sample size be for each resample? We want it to be 100, the same as the number of original trials. And how many resamples do you want? We want 10,000, so those are still kind of the same thing. And now what happens is, again, it creates the large matrix, except now it didn't ask us to separate our values by a comma. It actually it resampled from those 30 ones and 70 zeros. And you can see that if you look at these, you see predominantly zeros across each trial, and then some ones scattered about roughly around 30. And so now I can do the same thing as usual, resample mean of x. And all that's going to do is, in this case, it's going to calculate the proportion, right? Because it's going to be adding up ones and zeros, and that's going to be dividing by 100. So now you'll notice that you actually have proportions that are fairly around 30%, right? Because typically we would expect around 30 ones and 70 zeros to be resampled, but it's not uncommon. Look right there, you have a 35%. So now we just need to figure out how likely it is for us to get a 40%. So what we're going to do next is we'll do our resample hist. And there's the histogram. Notice that it's centered at 30. It shows the amount of variability, and 0.40 is over here. So that could mean that I'm going to be that to have 40%, that's going to indicate that there really is in fact a change. So I'm going to paste this as soon as it allows me to. And there it is. And again, I'm just going to say, okay, well, what's my cutoff? Well, since I'm doing a two-tailed test, I'm going to have a, and here I'm just going to draw the, since this is, we're doing alpha equals 0.10, that's the 10%, oh, excuse me, 10% not significance level, alpha level. That means 90% significance level. And so what that indicates to me is that this should be 5% here. This is 90%, right? Because if you have 10% error, then you're going to be 90% confident. And so the extra 10% has to be split equally between the two tails. So I'm going to calculate my cutoffs. Again, I'm going to do that much the same way. Notice this process is very similar, except we're simulating ones and zeros. And I'm going to do a percentile, 0.05. It tells me that I would expect something as low as 23%, which is, roughly around there, 0.23. And then that can be as high as, let's see, so now I want to do, well, this percentile up here, this is 5% plus 90%, that's the 95th percentile right there. So I'm going to calculate the 95th percentile, and it tells me that it's 0.38. So that's 35, 38 might be around there somewhere, 0.38. Okay, well, so that means that my sample value, these are cutoff points, so in order for me to decide that this proportion has in fact changed, I would need it to be either below 0.23 or above 0.38. Now, where does my sample proportion fall? Well, my sample proportion falls at 0.40 right there, which is in the tail. And so my conclusion, or I would say reject H naught, if P, my sample proportion, is either less than 0.23 or equal to, or if P is greater than or equal to 0.38. That's when I believe it will have changed. Since P is equal to 0.40, which is bigger than 0.38, we reject H naught. We believe that pi has changed. Well, how has it changed? It has increased. That's what we believe, right? Based on where it falls. It's much higher than we would expect if, in fact, the true proportion of people who go to a hospital for, what do we say, heart problems is, in fact, 30%. So what does that mean? That means that more than 30% seem to visit the hospital with these issues. We can't be sure, because it's still based on a sample, but we believe based on our evidence that that's true. So we can say also that we're 95% confident that pi is between 0.23 and 0.38. In other words, 23%, somewhere between 23% and 38% of people visit the hospital for this particular medical condition. So that's how we conduct a hypothesis test on for one proportion pi. And we'll do one more example where we'll consider, well, what if it's a one-tailed test? What would that look like?